You could fit over 1,000 Earths inside Jupiter. It is a massive, violent gas giant, and its sheer scale usually dominates our attention when we look at the outer solar system. But if you look past those chaotic, raging storms, you'll find a collection of small moons orbiting the planet that seem silent, frozen, and dead. One of the most fascinating is Europa. From the outside, it appears to be a shattered ball of solid ice, covered in deep, brownish scars. Beneath a 25-kilometer-thick icy crust sits a massive liquid ocean, plunging 100 kilometers down. To put that scale into perspective, this tiny moon contains twice the volume of all the water in Earth's oceans combined. This creates an immediate problem. Europa sits nearly 500 million miles away from the warming rays of the sun. In a deep freeze of that magnitude, an ocean of liquid water shouldn't exist. Finding a vast liquid ocean in the outer solar system challenges our understanding of the cosmos. If water can flow freely out here, we have to rethink the environments where life can thrive. If the sun's energy is too weak to melt that ice, a different engine must be generating heat to keep a 100-kilometer deep ocean from freezing solid. The source is the host planet itself. Jupiter exerts an overwhelming gravitational pull on everything caught in its orbit. This diagram illustrates Europa's path around the gas giant. Because the moon travels in an elliptical orbit, it constantly moves closer to and further away from Jupiter, subjecting it to a fluctuating gravitational grip. This process is known as tidal heating. As Jupiter's gravity continuously pulls and releases, it physically stretches and compresses the entire moon, much like a hand rhythmically squeezing a rubber stress ball. That continuous physical warping aggressively grinds the solid rock layers against each other deep within the moon's inner core. All that internal friction produces massive amounts of heat. This geothermal energy radiates upward, continuously melting the bottom layers of the ice shell to maintain the deep saltwater ocean. Ultimately, Europa operates as a self-sustaining thermal reactor. It proves that a planet's gravity can replace the sun as a primary energy source. In biology, there is a reliable indicator. Where there is liquid water and a consistent heat source, there is the potential for life. For decades, the scientific assumption was that even with heat and water, biology inherently required direct sunlight to function. But to see why that assumption is flawed, we only have to look at the extreme high-pressure depths of our own planet Earth. This is a deep-sea hydrothermal vent on Earth. Plunged in absolute darkness, these vents pump intensely hot, mineral-rich water out of the rock. Despite existing without sunlight, these vents are surrounded by thriving ecosystems. Vast colonies of bacteria, schools of blind fish, and specialized marine creatures survive purely on the chemical energy expelled by the Earth. Because Europa features a heated, rocky core interacting with a deep saltwater sea, it is highly probable that similar violent hydrothermal vents are actively pumping heat and life-sustaining minerals into its subterranean ocean right now. If darkness and geothermal heat birthed life at the bottom of our oceans, the same biological process could be occurring right now inside a moon of Jupiter. Europa's environment has made it the primary focus for modern space exploration. NASA developed the Europa Clipper mission to investigate that focus directly. The spacecraft will scan the moon's surface, accurately measuring the depth of its ocean and testing its salinity. The Clipper's main objective is to hunt for biosignatures, specific chemical markers that signal biological activity. It will search for organic molecules that may be venting through the cracks in the ice and spilling out into space. The spacecraft launches in 2024 and arrives in Jupiter's orbit by 2030. Within the next decade, we could have the data required to answer humanity's oldest scientific question. Finding even a single microscopic organism surviving beneath that ice would demonstrate that biology isn't a phenomenon unique to Earth. It would suggest that wherever the right ingredients exist, life is likely to follow.